This lesson is on balancing equations from substance names. So we've done balancing chemical equations starting with formulas, but now we're going to start with the names. So we're starting with hydrogen iodide yielding hydrogen gas and solid iodine. So we have to get the proper formula for our substance. So hydrogen to the left of the staircase, even though this is a molecular compound, we use the stock system to get the name and get the formula. So hydrogen, when it's in the front of a compound, is +1. Iodide, that is the iodide ion, which has a charge of -1. So we cross those charges and our formula is HI. Over here, we have to write the formula for hydrogen. And here we have to be very careful. This is neutral hydrogen in its elemental state, and hydrogen is one of the Hofbrinkel elements. So when it is produced in a chemical reaction, its formula is H2, not H, H2. Over here, hydrogen is in a compound and it's 1. It can be anything depending on what the compound is. But when hydrogen is by itself, then we have to have that 2 subscript. And let's review those Hofbrinkel elements because they're going to be really important for writing chemical equations. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. All of these, when they're by themselves in a chemical reaction, they must have 2 for a subscript. Plus, okay, so we have iodine. Iodine is one of our Hofbrinkels, so that must be written as I2. So now we can just balance as normal. 1, 1. Over here we have 2 and 2. So we put in a coefficient of 2, giving us 2 hydrogens, 2 iodines, and we're balanced. 2, 1, and 1. Remember, we need lowest whole number ratio for our coefficients. And also remember, once we have the proper formulas, we can't change subscripts. If we need more atoms, we have to do that by changing the subscript. Okay, let's look at our next example. So now we have aluminum plus bromine yielding aluminum bromide. So aluminum, it's by itself. This is elemental aluminum. It is neutral. And aluminum is not a Hofbrinkel. So we just write its formula as just Al. Bromine is a Hofbrinkel. So for bromine, we must write that as Br2, yielding aluminum bromide. So this is an ionic compound. So we're going to figure out our formula. So aluminum in a compound is a 3+ ion. Bromide, the bromide ion is Br with a -1. Cross our charges, and our formula is AlBr3. So now we have our formulas. Now we can go ahead and balance with aluminum and bromine. 1 aluminum on this side, 2 bromines, 1 aluminum on this side, 3 bromines. So our aluminum's okay, but we have this 2-3 situation. So remember, we're going to cross up so that we can get 6 bromines. So put a 3 here. 3 times 2 gives us 6 bromines on this side. Put a 2 here. Now we have to update the atom count for all the elements. So that gives us 2 aluminum, 2 times 3, 6 bromine. So bromine is good. Recheck our aluminum. We need a 2 on this side. Again, remember you put in a coefficient at this point. So now we have 2 and 6. 2 to 3 to 2 is lowest whole number ratio. And we're balanced. Oh yeah, I forgot to mention. Let's review our classification. So for this first reaction that we did just a minute ago, we have one substance breaking down into 2 more simpler substances. This is a decomposition reaction. And then the one that we just did, where we have 2 substances making a substance, this is a synthesis reaction, if we were to classify that. Okay, so our next example, we have silver nitrate aqueous plus sodium sulfide aqueous yielding silver sulfide solid plus sodium nitrate aqueous. Alrighty, so we have a lot of formulas that we need to do here. So silver nitrate, silver, it's to the left of the staircase. This is an ionic compound. So silver in a compound has a charge, so we have to remember our slide. Aluminum is 3+, we slide down to zinc, that is 2+, slide down to silver. Silver is a +1 ion in all compounds. And then nitrate from our polyatomic ion chart is NO3 with a -1 charge. We just cross down 1 and 1. Our formula is AgNO3. And aqueous means that the silver nitrate is dissolved in water. All right, plus sodium sulfide. So again, we have to figure out our formula. So sodium in group 1 is a +1 ion. Sulfide, that's the monatomic sulfur ion. It's not polyatomic. And this is a 2- ion. Cross those charges, so our formula is Na2S, also dissolved in water. All right, so our first product is silver sulfide. Silver, we already figured that out, is +1. Sulfide is 2-. Cross those charges, our formula is Ag2S. And that's a solid. This is a precipitate. Let's write that down. Precipitate. It is a solid formed when we mix solutions. All right, plus sodium nitrate. Sodium +1, nitrate -1. Our formula is NaNO3. And remember, when you have polyatomic ions in an equation, you can balance them as a group. So we just have to balance the silver, the nitrate ion, sodium, and sulfur. Over here, one silver, 1 nitrate group, 2 sodium, 1 sulfur. On this side, 2 silver, 1 sulfur, 1 sodium, and 1 nitrate. All right, we need to balance them. So we need to get 2 silvers, put in a coefficient. So we get 2 silver and 2 nitrate groups. All right, so now we need 2 nitrate groups on this side. Put in a 2. That gives us 2 sodium and 2 nitrate groups. 2, 2, 2, 1. Check our ratio, 2 to 1 to 1 to 2. That is balanced. And here we have 2 ionic compounds, changing ions to yield 2 different ionic compounds. Remember that this is called a double replacement reaction. And you might hear it called a double displacement reaction, but they mean the same thing. All right, our next example, we have pentane plus oxygen yielding carbon dioxide and water vapor. So pentane, this is a hydrocarbon. The ane means we have all single bonds, and the pent means that we have 5 carbons. So you might remember that formula, or if you don't remember it, we can just figure it out. So the pentane means we have 5 carbons. 1, 2, 3, 4, 5. Ane, again, all single bonds to the hydrogens. Carbon takes 4 bonds around it. So we're just going to fill in hydrogens so that every carbon has 4 bonds. All right, now we can just write our formula. C5H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is our formula. Oxygen is a HOF Brinkle. So this must be O2. Carbon dioxide. Carbon is to the right of the staircase. This is a covalent compound. We can see that the prefix system is being used. So carbon CO2, and water vapor is H2O, and the vapor means that it's in the gas phase for this particular reaction. Okay, so this is what I call a CHO reaction. So we're always going to do carbon first, then hydrogen, then oxygen. So on the left we have 5 carbons, 12 hydrogens, and 2 oxygens. On the right, 1 carbon, 2 hydrogens, and 3 oxygens. We want to balance carbon first. We need 5 over here. Put in a coefficient of 5. That gives us 5 carbons, and 5 times 2, 10, plus 1, 11 oxygens. Okay, we're always going to do hydrogen next. We need to get 12. So if we put a 6 in front, then 6 times 2 gives us our 12 hydrogens. And then for our oxygen count, 5 times 2 is 10, plus 6 is 16 oxygens. So now we need 16 on this side. So put in an 8, because 8 times 2 is 16. 5, 12, 16. Our ratio 1 to 8 to 5 to 6. We are balanced. And this type of reaction where we have oxygen as a reactant and we get carbon dioxide and water, specifically this is combustion of a hydrocarbon. So this is combustion. And just like with the Bunsen burner, if you have this reaction, you're going to get heat and light. You'll get energy from this reaction. So, sometimes you might see a sentence describing the chemical reaction and you need to write the reaction. So, we're going to look at this one. So, in industry, solid titanium is produced by reacting titanium Roman numeral 4 chloride. In industry, they call that compound TiCl with liquid magnesium, and they call that Mag. Magnesium chloride is also produced in the reaction. So we want to write our equation. So we have to figure out what the reactants are and what the products are. So this is telling me solid titanium is produced. So if I write my yield sign, titanium goes on this side of the arrow because it is a product. By reacting titanium Roman numeral 4 chloride. So this is a reactant. So titanium Roman numeral 4 means it is a 4 plus ion. Chloride is a -1 ion. 4, 1. So our formula is TiCl4. All right, so we're reacting the titanium Roman numeral 4 chloride with liquid magnesium. So magnesium by itself, elemental magnesium, doesn't have a charge, and it is not a Hofbrinkel. So that's the formula, just like that. It says magnesium chloride is also produced, meaning magnesium chloride is a product. So magnesium, 2 plus ion, chloride -1, and our formula is MgCl2. Now you can go ahead and balance as usual. So we have 1 titanium, 4 chlorine, 1 magnesium over here, 1 titanium, 1 magnesium, and 2 chlorines. So we need to balance up the chlorines. To get 4, put a 2 in front, our coefficient. That gives us 2 magnesium and 4 chlorines. All right, titanium's still good, chlorine is good. Now magnesium, we need 2 on this side. Put in a coefficient of 2, and we're balanced. 1 to 2 to 1 to 2 is the lowest whole number ratio. And if we look at this equation, we have an element and a compound. And magnesium is booting out the titanium to get titanium by itself and then making a different compound. So this is a single replacement. Reaction. All right, I think that's it. Oh no, I've got one more. Okay, well that's good. When solutions of calcium chloride and sodium phosphate are mixed, a precipitate of calcium phosphate is formed along with aqueous sodium chloride. All right, so you always want to like read it first, kind of get an idea of what's going on, and then go back and analyze it. So solutions means our substances are dissolved in water. So the calcium chloride and sodium phosphate are being mixed. They are the reactants. So let's write our formula. So calcium chloride, calcium, 2 plus, chloride minus 1, cross your charges. So we get CaCl2. And it's telling us that's a solution, so we can write aqueous down. Our other reactant is sodium phosphate. So sodium is a +1, phosphate, PO4, 3 minus. So our formula is Na3PO4. Oh, and I didn't need to put those parentheses, so you can have them or not have them. And this is also dissolved in water, so that's AQ. All right, a precipitate of calcium phosphate is formed. That means that the calcium phosphate is a product. So calcium 2 plus, phosphate 3 minus, cross, we get Ca3 parentheses, PO4 parentheses 2. This time I absolutely need those parentheses. And it's a precipitate, so that means that it's a solid. A solid is formed from solutions. Then up here, along with aqueous sodium chloride. So sodium +1, chloride -1, 1 and 1. We get NaCl, and it tells us it's aqueous. That means it stays dissolved in the solution. All right, so now we have all our formulas. Now we can just go ahead and balance as usual. Calcium, chlorine, sodium. I'm going to balance phosphate as a group. And phosphate. On this side, 1, 2, 3, 1. And on this side, I have 3 calcium, 2 phosphate groups, 1 sodium, and 1 chloride. All right, I need 3 calcium over here. So that gives me my 3 calciums, and 3 times 2 gives me 6 chlorines. All right, so I need 6 chlorines on this side. So let's put in a 6, squish it in there. That gives me 6 sodiums and 6 chlorines. All right, so the next thing I need to balance is the sodium. I have 6 on this side. I need to get 6 on this side. So if I put in a 2, and I have 2 times 3, I get my 6. And that also means I have 2 phosphate groups. And everything balances. 3 to 2 to 1 to 6 is lowest whole number ratio. That's good. And to identify the type of reaction, 2 ionic compounds in the reactant side, 2 ionic compounds in the product side. This is a double replacement reaction. Okay, and that truly was the last one.